Hello, everyone, and welcome to this episode. Today, we're working through some multiple choice questions on the properties of solids, and this is AP Chemistry section 3.2 on the syllabus. So it can be kind of difficult because, again, just like intermolecular forces in 3.1, you have to be able to imagine the forces of attraction between molecules and ions, the type of bonding that occurs in each of the different types of metals, and how that translates into the macro world of its physical properties, things like hardness and melting point and conductivity and so on. So there's a lot of conceptual things here, not a lot of math going on, but we just have to sort of get through it, and we're going to get through a few questions today, and I hope you find it helpful. Before we get into the questions, I thought we'd take a look at a table something like this. And you might have a table like this. There's plenty of them on the internet. I highly recommend getting one if you don't have one already, and kind of working your way through and just getting familiar with what's on here. It lists the types of metallic solids, types of solids: metallic, ionic, network, covalent, and then three types of molecular solids or covalent: nonpolar, polar, and hydrogen bonded. It also lists what their structural particles look like, whether they're cations and delocalized electrons for metallic elements, cations and anions for ionic, single atoms for network covalent, atoms again for non-molecular compounds or nonpolar molecules, polar molecules, or molecules with H bonded to N, O, and F. And it's just going to be one of those things where you just have to do it enough times where you kind of get familiar with it, and then you can start imagining what the crystals of these substances look like. It can be a challenge. It might take some time. For some, it takes less time than others, and we just have to be where we are and do what we can with it. So let's go through real quick so we can have some background. Metallic solids are those cations with delocalized electrons in that sea of electrons. That's called metallic bonding. And in terms of their properties, hardness varies. Okay, it's going to be a wide range of hardnesses, and that's not very helpful. I'm sorry about that. Melting point varies from very low to very high. Again, not that helpful. But the idea here is that it is lustrous, ductile, malleable, very good conductors of heat and electricity. Those are the ones you're going to want to look for because those are the ones that set them apart as metallic solids. Ionic solids are made up of electrostatic attractions between cations and anions. They have crystal structures alternating one of each at a time. They are pretty hard, moderate to high melting points, so we're getting somewhere on those. Non-conductors as solids, but good electric conductors as liquids. So when those get melted and the ions can move around, that's going to be a good conductor. Many are soluble in polar solvents like water, and they conduct electricity in a solution as well. Network covalent compounds. Those are the ones that are like glass or silicon or diamond, where they have covalent bonds in all three dimensions, and it goes on and on and on. These are very, very hard usually, and either sublimate or melt at very, very high temperatures. So like diamond melts at like over 3,000 degrees, which is a lot. Most are non-conductors of electricity, and they're just very hard. So that's that. In the molecular solids section, we have London dispersion forces as the main force here for the nonpolar ones. They're soft, extremely low to moderate melting points depending on molar mass. Sublime in some cases, they're soluble in usually nonpolar solvents. So there's a lot on here, I know, I'm sorry. Polar has dispersion forces and dipole-dipole attractions, low to moderate melting points, not extremely low, but low. Soluble in some polar and some nonpolar solvents, depending on what it is. And hydrogen bonded, low to moderate melting points, soluble in some hydrogen bonded solvents and polar solvents. So it's a good idea. Just spend some time with it, I guess. And the more you do these practice ones, the better it will be for us. All right, let's get started. We'll do a couple of pause the video moments along the way as well. So here's our first example. Pay attention to the descriptors in these questions. They are the clues that give you what you need. A sample of a hard, solid binary compound at room temperature. Compound, so it's not necessarily a metal, at room temperature did not conduct electricity as a pure solid, but became highly conductive when dissolved in water. Which of the following types of interactions is most likely found between the particles of the substance? If we paid attention on our chart a minute ago, we know that The only kind that fits that is the ionic bonds, because when they are solid, they don't conduct electricity, but when they become ions floating in the liquid, they're conductive. And so that's ionic bonding. Okay, let's do another one. Which of the following could be the identity of a white crystalline solid that exhibits the following properties? It melts at 320. It does not conduct electricity as a solid. It conducts electricity in the aqueous solution. So again, this is a little bit deeper because you might recognize some of the same things. Hey, this looks like ionic, but which of these is ionic? And so you have to kind of know a step further and know that ionic compounds typically contain metals as ions, like cations, and nonmetals as anions. And really the one that contains the anion, cation, and an anion, rather than just the cation, is the sodium hydroxide right there. If at any point you have any questions, you can always send me in the comments or send them directly. In the meantime, let's take a minute and do a pause the video moment. Take a moment. A solid is tested in a laboratory to determine its properties. Which of the following provides the best evidence to support the hypothesis that the solid is a metal as opposed to a nonmetal? So think about the properties of metals. Which of those best supports it? Great. And if you paused the video and thought about it and found out that B is the thing that is characteristic of metals, then good job with that. And on to the next question. A certain crystalline substance that has a low melting point does not conduct electricity in the solution or when melted. That's the key, or when melted. This substance is likely to be a covalent network solid, metallic solid, ionic solid, or molecular solid. So we're looking at clues. Low melting point. That tells me it's definitely not a covalent network solid. It might be a metallic solid, like mercury has a very low melting point. An ionic solid, they're typically high, so I'm going to rule out A and C first. But it does not conduct electricity, and metals tend to conduct electricity, so that by process of elimination is letter D, a molecular solid. Next one. Which of the following best explains how the bonding in a metal allows it to be ductile? So it allows it to be drawn into a wire. You can change the shape of metals by hammering them into shapes or bending them into shapes or twisting or stretching. Metal atoms are spherical, therefore the solid metal can be easily drawn into wires. I mean, yes, they are generally spherical, but I don't know if that justifies anything here. Because of strongly directional bonding in the solid metal, the atoms both in front and behind will bind together more strongly. So metals have non-directional bonding. Those electrons are kind of free to move throughout the sample, and they're kind of going in all directions. So the metal cores are equally attracted in every direction to those electrons. And here we have C, because mobile electrons attract the metal equally in all directions. The metal cations can move easily past one another as the metal is drawn into a wire. And the size doesn't matter there. So yeah, letter C is our answer on that one. All right, second pause the video moment. We have a drawing of a solid structure. Which of the following most likely describes the solid represented in the diagram above? Take a moment, pause the video, be back in a couple of seconds. Okay, so I look at the diagram and I'm seeing negative anions, positive cations. And if I see both in this type of form, it's definitely an ionic solid. And the one answer that correctly sort of summarizes ionic solid is this letter C. It's brittle. It'll snap into cleavage and all kinds of stuff. And it's water soluble usually, sometimes not. That's a poor electrical conductor as a solid. Yes, it'll conduct in solution, but not as a solid. And in our next question, methane makes an appearance. In solid methane, methane is usually a gas. It's natural gas. The forces between neighboring CH4 molecules are best described as covalent bonds, hydrogen bonds, ion dipole forces, London dispersion. So this is kind of like an intermolecular force question again, but we're talking about solids here. And so in order to go between molecules, intermolecular forces, we have to be able to identify, well, what shape is this molecule and is it polar or not? And it may be the kind of thing where I highly recommend, if you don't or can't visualize a molecule just from your experience, take a quick moment and draw it. And if we draw it correctly, we see that it's 4 bonds, 0 lone pairs. It's tetrahedral, non-polar because all the hydrogens are the same. And so it's non-polar. The only intermolecular force that it could have is London dispersion forces. It would not have covalent bonds to other molecules because then it would just be one big molecule. And we're talking about just methanes here. So there we go. And more words on this one. Which of the following best helps to explain why CCl4 is a liquid where Ci4 is a solid and when both are at 25 degrees Celsius? So we've got 2 similar molecules. They're both, if you took the time to draw them, they're both tetrahedral, carbon in the middle, 4 chlorines, and 4 iodines around the end. So the dipole moment of CCl4 is larger than the Ci4 because Cl is more electronegative. Well, yes, it is, but it's a non-polar molecule, so it doesn't really, it's evenly distributed. The dipole moment of the Ci4 molecule is larger than that. Again, there's no dipole moment because it's a non-polar molecule, so let's get rid of that. The London dispersion forces are stronger in CCl4 because Cl is more electronegative. Now we're getting somewhere. The London dispersion forces are stronger in Ci4 because Ci4 has a more polarizable electron cloud. And yes, they're similar molecules, but the iodines are bigger, a lot more electrons, 53 as opposed to 17. And so that means a larger dipole, or London dispersion. Sorry about that. All right, your turn. This is our third pause the video moment. We'll have one more in a little bit. At room temperature, iodine is a molecular solid. Which of the following provides a characteristic of iodine with a correct explanation? Take a moment, pause the video, and be back in a couple seconds. And we have these choices. High melting point because it has a weak intermolecular force. It's hard because it forms a 3-dimensional covalent network. Definitely not that one because iodine is just I2. That's the formula. It's not a good conductor of electricity because its valence electrons are localized in bonding and non-bonding pairs. So maybe that one. It's very soluble in water. Okay, not polar molecules, so that's not going to work. We already ruled out B. Will it have a high melting point? I mean, it is a solid at room temperature, but a high melting point would mean strong intermolecular forces and not weak ones. So yes, letter C is our correct answer. It's not going to conduct electricity. Okay, sometimes you may run into a question like this, where they give you some choices here and maybe 3 or 4 questions in a row that refer back to those choices. And they do this thing that's kind of annoying sometimes where it says a choice may be used once, more than once, or not at all. Don't you hate that? You want to just be able to check it off the list and narrow your choices down, but we have to have an extra challenge, I guess. So let's just do one of these. Solid ethyl alcohol, C2H5OH, is one of those 4 from this list. So how do we know what it is? So I'm thinking carbons, hydrogens, and oxygens, no metals, so it's not ionic. Okay, so get rid of that one. And it's not a network solid because that usually has all the same atoms, or sometimes SiO2 or something like that. And we got a molecular solid with 0 dipole moment, molecular solid with hydrogen bonding. And I'm looking at this baby over there. That OH is telling me hydrogen bonding because the hydrogen is attached to an oxygen. So nobody gets mad at me. I'll circle the right answer. All right, this next one made me look twice for a short amount of time. They give us 2 structures. And I looked at them and I'm like, oh, those are ionic. That's great. We got some cations, anions, and so on with these little sticks between them. And it says, which element correctly identifies diagram 1 and identifies the compound with the low melting point? Why? NaCl, MgS. So binary ionic compounds. And I don't know about you, but I really had to look at this one carefully because I'm seeing these larger anions and these smaller cations, and these both look binary to me. And I'm supposed to guess which one of these contains the white for the chlorine and the shaded for the sulfur, or vice versa, and which ones are the metal cations. It took me a moment, but then I realized that these little metal cations are a little smaller than those metal cations. And that tells me that those metal cations are probably the magnesium 2+, as opposed to the sodium plus, because the higher the charge of the cation, the smaller the ion is going to be. And also, if you squint really hard, those look a little bit bigger than the chloride ions. So I'm going to guess that those are the sulfur sulfide ions. So that means diagram 1 is NaCl. So that means I can get rid of those two. Process of elimination. Great. So it has a lower melting point than MgS because the coulombic attractions between the singly charged sodium and chlorine are stronger. So we're looking at lower, stronger. And then we have lower and weaker. Which one of those is the best? Otherwise, they're the same answer to the same question. Turns out, lower melting point means weaker coulombic attractions. That's what makes it a lower melting point. They're not held together very much, and that makes it letter B on that one. All right, we got our last pause the video moment. A little more challenging one for you guys, but take a moment and check it out. We got boiling points of NaF and MgO, ionic radii of a bunch of different things here. Based on the data in the table above, which of the following statements provides the best predictions for the boiling point of NaCl? Not that one, but some combination. And they give us some choices. Lower boiling point than NaF, boiling point between the two, higher boiling point than MgO, higher boiling point than MgO. And take a moment, pause the video, read through them, and see what you think. All right, and if you came up with the correct letter A, then congratulations, that was a tougher one. And it happens to be letter A because it does both contain sodium, but a chloride ion is larger in radius than the fluoride ion. So the sodium and chlorine are not going to get as close to each other, therefore they're not going to release as much energy, and it's easier to take them apart. The closer the nuclei get to each other, the harder it is and the higher the melting point is for that substance. Magnesium oxide is much higher because it's got a +2 and a -2 as opposed to a +1 and a -1, so that's very good. Sodium chloride is +1, -1, but again, because the chlorine is bigger, you'll get weaker coulombic attractions, and none of these are correct as well. So if you got that, congratulations, and I hope you found helpful these examples of multiple choice questions that contain solids. It will appear somewhere on your AP exam. So take the time to just get some practice and sort of learn those overarching general properties of solids, because that will come in handy. Thanks for watching this episode. I hope you found it helpful. If you have questions, send them to me in the comments or directly. And in the meantime, happy studying and have a great day.